Okay, so quantitative analysis can seem intimidating at first, but it doesn't have to be that difficult. The important thing is that you need to start with known quantities. That is number, data, or statistics, but those known quantities need to be accurate. Garbage in, garbage out. Are accurate numbers, accurate data or statistics that tell you how often your identified hazard is actually responsible for a mishap. Historically, how often has it been responsible for a mishap? Once you have that information, the rest is really not that difficult. So remember our risk equation. The risk equation has the two elements, right? Severity and probability. As we discuss quantitative versus qualitative analysis, we are only dealing with the probability side of the risk equation. So in science, it is generally thought that if you have numbers or statistics on something, you know more about that thing. So as we discuss the probability side, when we debate whether to use quantitative or qualitative data techniques to generate our probability, science often will say numbers makes your analysis more accurate. But be careful with this paradigm. Quite often, well-defined qualitative probability can just as well get the engineer to the same level of accuracy for making risk-based decisions. Quantitative data, it must be accurate in order to accurately use that data for decision making. Quantitative analysis is generally more time-consuming and more costly than qualitative analysis, and sometimes it may be preferable to qualitatively analyze hazards into risk, and then the engineer may choose to conduct quantitative analysis on some of the higher level risks in order to help prioritize the risk reduction efforts. But let's get into the meat and potatoes of this quantitative analysis. When it is appropriate to use quantitative analysis, here's how we do it. The probability level is generally expressed as a ratio. It's a ratio. It's 1 in every 10, or 1 in every 100, or 1 in every 1 million. It's a ratio. The numerator is the actual or expected number of mishaps. In other words, 1 mishap in every 10 occurrences. The denominator is that number of occurrences, or the exposure. Okay, so the actual number of mishaps, the numerator, the denominator being the exposure. There will be 1 mishap in every 100 occurrences of the item. All right, so quantitative then is a ratio and is generally expressed as a power of 10. Don't let the power of 10 be intimidating. That one, I have a little trick that I like to remember what it actually means, and that is the number in the superscript is the number of zeros, except that it's also the 0 before the decimal place. So 0.01 would be the 10 to the negative 2. 10 to the negative 2 has 2 zeros and then the 1. So it's 1/100th, but 10 to the negative 2, 2 zeros, 0 before the decimal place, and then the second 0. That's just how I like to remember it. 10 to the negative 4, again, would have 1 0, a decimal place, 2, 3, 4, and a 1. So 0.0001 would be 10 to the negative 4. So that's how I like to remember the power of 10. It just keeps it a little bit handy for me. The example that we give in the PowerPoint is that of commercial aviation. In commercial aviation, we say 2 accidents occur. It's been said that fewer than 2 accidents will occur worldwide for every 1 million departures. Let's make that into a quantitative probability. So we have 2 accidents occur. That is the numerator. That's the number of actual mishaps. All right, the number of actual mishaps. 2 accidents occur for every 1 million departures. That's the specified exposure. So every 1 million departures, they say 2 accidents might occur. We express that first as a ratio, 2 to 1 million. Divide those out, and that becomes 0.000002. Okay, the probability factor then is less than 10 to the negative 5. That's less zeros, but this one has 5 zeros in it, including the one before the decimal point, and greater than 10 to the negative 6. That's 1 1/millionth, and that is 6 zeros. So the probability is between those two, between 10 to the negative 5 and 10 to the negative 6. Or we'd say it's less than 10 to the negative 5, greater than 10 to the negative 6. How does that translate into English, you might ask? Here we go. Here is from your your government documents, MIL STD 882. It gives this example of probability levels, and it has both qualitative probability levels here on the left side and quantitative probabilities here on the right side. In our scenario, 10 to the negative 5 to 10 to the negative 6 falls in the remote, which is D level, if there's a remote chance of occurrence right there. So our previous slide, we determined that two accidents, two possibilities of a mishap in every 1 million occurrence yielded a probability of a remote occurrence. So if it's remote, why should we worry about it? Remember that probability is only one side of the risk equation, and that is all we're talking about here. Severity also factors in to determine our risk level, and thus we still need to compare the two to make sure they are at an acceptable overall risk level. Two more quick things I wanted to point out. Check out the improbable level. Probability of occurrence of less than 10 to the negative 6. That's less than 1 in 1 million of occurrence. We still discuss such low probability levels in high-risk operations. And remember that no amount of zeros, no matter how low of a probability, not even a probability of 1 in a billion, will allow us to select eliminated as a probability unless the hazard is actually no longer there, which means it would be designed out.